Welcome, everyone. My name is Pia,
And I'm Dave,
and we do this together.
teaching the Science and Cooking lecture series. So how many people have been to this lecture before, this lecture series? Ooh,
Nice.
Everybody, great. Okay, so you know the rules. So anyways, it's really a pleasure to introduce José Andrés. We've known him for a long time. We've known José since the inception of the class, and he is really just a wonderful, wonderful person. We know him in many different ways.
We know him as a teacher. He's been sitting here. He's been sitting on this bench right here explaining about emulsions and alginate and diffusion.
And let me tell a little story. I went somewhere with José and Michael Brenner, another professor who was at the inception of the class, and we were trying to teach high school students about surfactants. And we looked at each other, and José looked at us and says, "You don't know how to do it?" And he got up and he told the science of surfactants to high school kids much better than Michael or I could do. He's a wonderful teacher. He's a wonderful chef. And he's also really a wonderful humanist. And for that reason, he's not here today because he's still in Jamaica trying to take care of what's happened there.
Which is sad.
Which is sad.
But we do have an amazing team who will make up for it, and they will wow you all, including us. So the focus of this week, and you know how we usually have a science topic for each week, and the focus for this week is emulsions and foams, which is one of my favorite things, but I know that it's really, really, really one of Dave's favorite things. The very first thing I learned to cook was a salad dressing. That's an emulsion. One of my favorite sauces is a hollandaise sauce. So good. That's an emulsion. Mayonnaise is an emulsion. And what about foams? You like foams?
I love foam. So this is what I have every morning. This is my dessert. And this, will you join me for one of these after class?
Sure.
What about this one, Pia?
And ice cream. Ice cream is beautiful in that it has all of this come together. It is an emulsion. It is a foam, and it is also something called a colloidal suspension, which you may know of if you've come to these lectures before.
And so what really amazes me about emulsions and foams is that this is an emulsion. It's a mixture of two fluids. Fluids, they flow everywhere. But you mix them together, you just mix them, and you end up with a solid. And a foam is even more amazing. You mix air goes everywhere, and water, and you mix it, and again, you end up with a solid. How can that happen? That's what's so amazing about these materials. And the reason is they become elastic because of the bubbles or the drops. You have to deform them. And I think this is a little movie. As you deform them, it takes a force. You store energy in them by deforming them. It takes a force. As you pack them together, you deform them, and that gives you some energy. That gives you the elasticity. And the more you pack them, the more elastic they are. And so, whoops. My clicker clicks too fast. I'm going to just go back and show you what I wanted to show you. Sorry. There's a delay. So if you push them together, you see the way they're deformed? All the drops are deformed. You have to push them together. You have to make sure they touch. And if you have just a few drops, just a few bubbles in a fluid, they won't touch. And they'll flow. They're liquid. But as you squeeze them more and more, above a certain volume fraction, a certain amount of the bubbles, they begin to touch and they begin to deform. And that's what gives them the elasticity. And that's the elastic equation. Yeah, you can clap again. Those of you who know, you have to clap for an equation in this class. And so this is made up. I don't need to go through the details, but this depends on the surface tension and the radius of the drops and the volume fraction. If I go back here and look, you have to be above the critical volume fraction. Then it just increases linearly with the amount of extra volume fraction. So here's This is a week of foams. This is a wonderful foam. This is egg white. This is something that Joanne Chang makes. We have it many times. It's a beautiful whip. Look how solid it is. It's just mixing air into a fluid, and you end up with something solid. If you look at an image of this, you see how they're deformed. This is actually, interestingly, Pia told me, this is not the foam that I just showed you. It's a mayonnaise. A mayonnaise is water or oil drops in water, liquid in liquid. If I make it with a foam, if I make it air in liquid, then tonight, just to give you a little bit of a preview, we're going to cook under gravity, under increased gravity. So if I put this under increased gravity, I'm pushing on it with gravity. I can't squeeze the water, but I can squeeze the air. And how much force does it take to squeeze the air? Exactly 1 atmosphere. And you'll see they put many G's, many atmospheres. And so you'll see the whole behavior of anything that's a foam will change because you can squeeze it. It's not something you'll see if you mix it and you look at it at normal gravity. It's only when you go above 1 G, which is what you're doing here. So it's a very interesting thing. You'll see, and we'll hear a little bit more about this. When you cook under high G, you have to do it differently if it's a foam than if it's an emulsion. And so Jose can't join us, but he did send us this video.
So everybody, I'm so sorry, Chef José Andrés, I cannot be with you here today, but I hope you understand I'm in Jamaica, in a place called White House. Yeah, White House. White House, beautiful Jamaica, unfortunately of destruction. White House is very much ground zero. One of the most powerful hurricanes is low, and the hurricane generates a lot of centrifugation. That centrifugation, well, today you're going to see how that can be a destruction, but that can be created for something good. The most important for me, though, is this very simple thought that I love those classes. Since the first day I came with my friend Ferran Adria to meet Dave, the most amazing professor, everybody, all the professors. I don't want anybody to get jealous. And all the assistant professors. And for me it's been great because I learned so much. And I used to come every year, every class, more than one, every semester, more than one class. And I love it. But it's good to give room to others. So, you know, today's emulsions. And I don't know if you saw, but in your Rogan I made this amazing omelette emulsion, I would say, because it was a mayonnaise. Most stable of emulsions, at least in the culinary world. Even, you know, a mayonnaise can be also a foam if we put it with N2O, but that's another conversation. But in your Rogan I was able to make this amazing omelette with egg white, with egg and mayonnaise, equal egg to equal mayonnaise, and makes one of the most amazing emulsified omelettes in the history of mankind. And today, I know Professor Dave is going to talk about it, but today we have we have some of my amazing team. Charisse Dickens is in the house. Yes, you can give a big round of applause to Charisse. Say hi, Charisse. Jim Sears is in the house. Give a big round of applause to Jim Sears. And you know that my team and I, with Charisse, not too long ago we sent food to space. Paella, that we did it so traditionally correct that when they opened it in the space, the grains were floating. And yeah, and then you understood why chopsticks are good for, to pick each one in a space. Imagine failure engine because José Andrés and paella to space. Oh my God. Yeah, food needs to be moist in a space. But anyway, everybody will say, why you are spending time thinking about feeding people in space when actually you are in Earth feeding people in a hurricane? Because sometimes the same technology can be helping you to do both successfully. In Ukraine, we serve food with the same technology we used to send to space, you see? Helps you fight hunger, helps you feed people in space. Always, 1 + 1 is 3. more important. Because our love to space, we met this amazing genius, Jim Sears, and I mean, my driver is kidding me in the middle of my video. I don't know why. He keeps kidding me every time. And well, she's Jamaican. It's total darkness. It's no one light anywhere. But people are hopeful. But let me go back. So my friend Sears, he loved like me. Space. But he loved space a lot. So much that he's thinking how we're gonna cook in gravity zero in the space station. And he created a kitchen. I'm not gonna tell you more about it, but he shared with us two of the first prototypes, and we've been able to do a lot of recipes using this amazing machine. But I can tell you all about this machine. But you have an expert plus Cherise plus Dave plus whatever we are gonna cook with emulsions on that kitchen. And only to say that today you have an amazing class. The only sad thing is I'm not there with you. So I'm gonna stop rambling. Love you. I know in every class they give you a formula, and I didn't prepare any formula. But I think my formula today, you know, today we've done a lot of emulsions because I put some mayonnaise on sandwiches, so, and we make those sandwiches with love, so, and I think we gave hope. So I guess this is gonna be love plus hope square equals a better tomorrow. That's my equation of the day. Bye. Beat that, Dave.
Okay. Thank you, Jose, out there. Thank you for what you're doing. So what I'd like for you to keep an eye out for is that since so many foods are emulsions and foams, when you are cooking them and when you're trying to cook in space, those are the materials you're manipulating. And now suddenly you're manipulating those, like that's hard enough here on Earth. But imagine you are no longer on Earth and most of the laws don't apply. Like this is the contraption that will help you do that. So I want you to think about that, and I want you to keep an eye out for bubbles and droplets that appear in these foods. Beautiful. Okay. So with this, let me introduce this amazing team that we have, even just in the last 3 hours. We have learned so much from these three, and we have already had so many interesting conversations. I can't wait for you to hear about this. So Chef Cherise Gray, who is the Senior Director of R&D, Sam, who is the Senior Editorial Director, and then Jim Sears, who is the brain behind these amazing little ovens, let we call them, they're together going to show us how all of this is going to work and how we're going to cook in space. So let's welcome them.
So I'm Sam. Thank you for having us here tonight. Briefly, just want to say that the first time Cherise and I were in the same room was in this room in 2011 during Jose's lecture, and that's the first time I met Jose as well, so it feels like a good full circle moment. We've been doing this, Cherise and Jose have been doing this for a few years now, right?
Yeah. So Jose is friends with Michael Lopez Alegria. He is a Spaniard, their countryman, and Michael Lopez not only was a very decorated NASA astronaut, he went to the private sector and joined Axiom. And for the first manned mission to the, oh sorry, not the manned mission, for the first private mission to the ISS, he wanted to make this visit really special for Axiom and for the crew members of the ISS at the time. And so he approached Jose telling him, hey, you know, I really want to make something nice. I want to do, in the hospitality industry, we call it family meal. It's, you know, we basically make food for everybody in the restaurant. You know, ideally, we all have about 5 minutes to sit down, enjoy a meal together. And so taking the spirit of a family meal, Michael was really inspired to put that idea into space. So talked to Jose about some opportunities that we could have for dishes. And of course, Jose's mind immediately went to paella. Not a bad choice. But, you know, it was such a unique opportunity. I think, you know, we ended up sending 2 actual formulas, so 2 recipes into space. And while they were delicious in their right, you know, they are, you know, I don't know if you guys are preppers or if you guys have been in the military
or
or if you guys have ever done any humanitarian work. You've probably had a lot of experience with something called MREs, right? Like these
Has
are.
anybody ever tried an MRE? Yeah. How are they? They're great. Oh, thumbs down. No, they're not great.
They're great depending on how desperate you are for some calories.
Well, yeah, they're really important in they serve a purpose. And Charisse, actually, what is that the?
So
what is
yeah,
that?
this is actually the last living pouch of the paella that we sent up.
What vintage is that?
2021.
That's a good year, right?
Yeah.
A good year for
It was a
paella.
good year. It was out of this world.
Out of this world.
So this is
Can we
the
taste
last
that
living
tonight?
pouch. We cannot taste this. You know, Sam and I made jokes about this, about, you know, oh, if Jose was here, he'd want to open this pouch, to which I would have to reply to Jose is like, that this belongs to the Air and Space Museum. You know, like having a chef, somebody like Jose in an exhibit, you know, just because of the humanitarian work that he does and how this can actually provide and sustain and provide nutrient for not those just terrestrially, but those that are in space as well. And so this is a very strong representation of Jose and really speaks to the spirit of what he does. So this will not be open. This is going to go under my pillow tonight to be sure nobody can actually access that. So,
The next year, a couple years later, we kept working with Axiom.
2 years later, we actually, after doing the work and figuring out how to formulate here, there was a lot of discoveries that we had and ways to improve, but we thought that the most important thing we could do is actually go and work with the actual crew members. So while we sent food up in AX1, for AX2, which was the following mission, we quarantined with the crew members, and we basically lived with them for 2 weeks, and we provided every single meal for them, breakfast, lunch, and dinner. And it was because we wanted to understand the relationship that they have with food. A lot of times you hear from engineers and from some people in NASA where, you know, food is just calories. It's just a calorie that has to be met. And we argued that that is not true. And when we did our AX2 mission when we did our quarantine with AX2 mission, we were right. Because everything that they asked for, it was Mother's Day. I won't forget it. It was Mother's Day, and they were launching, I think it was about 4 or 5 days after Mother's Day. And, you know, it's daunting, the fear of, you know, doing something like that, you know, strapping yourself to a few kilotons of, you know, fuel and jettisoning yourself into space. Like, it's a little bit scary. So we actually asked the crew members and everybody that was in quarantine. It wasn't just the crew members. It was their fitness instructors. It was everybody that was attached to the quarantine. And we asked them all, hey, like, it's Mother's Day. What's the one dish that your mother made for you that just immediately you think about her? And with that, we actually made every single dish that night. So they had like a Mother's Day meal, but it was like so touching because they were all like, some of them are crying.
So what we've learned from that experience and all the research we've done about this is not just the physical health. You know, we have to be feeding the body on these missions, but also feeding the soul and feeding the heart. And that's obviously something we see what Jose is doing in Jamaica, what he's done for years and years and years with his World Central Kitchen work. So as we start to think about what space travel turns into in the future, it's not just going to be a short trip on the ISS. It's not just going to be in a few years, hopefully going to the moon and back, but it could be longer haul missions to Mars. It could be colonizing the moon or Mars. It could be, you know, it could be space hotels where people go up for fun for a week. But we want all these people to be eating good food. So, boom, the final frontier.
In comes Jim.
Jim?
Okay, boiling water. So cooking has always begun with boiling water. People have started cooking like hundreds of thousands of years ago. And a lot of it was just kind of on fire and things would get burned. But boiling water like changed the equation. And before they had pots, they had like skins. And the skin would be sitting there, you put water in it and the food that you want to cook, and then you put hot rocks in it until the water boiled. And the magical thing about boiling water, it is kind of magical, is that the steam, every time it hits something, it condenses and makes it exactly 100 degrees Celsius. So no matter what crevice, everything goes to 100 degrees C, boiling point. And that's the miracle of cooking, that all the food gets sterile, gets pasteurized, and so you eat and gets digestible. So boiling is fundamental. And you can't do it in space, but, well, maybe you can. You know, the problem with space, and, you know, use the hook if I get to, I can just geek out on water.
We'll keep you tame, James.
The difficulty in boiling water in space is, besides the fact that the pan would float off, right? If you keep the pan, so keep the water in there. As it started to vaporize against the hot surface, it would separate from that surface, and they have pictures of this in space, just make a large, like, bulbous globule of steam, and it would dry out, it would pull away, and you couldn't even get any more heat into it because there'd be no water touching the hot part. So we're going to show you how we can boil water in zero G by making artificial G and forcing that water against the hot surface. So it's really pretty geeky cool.
Can we get the camera?
So yeah.
How's our water looking, Charisse?
We're ready. I think if you want to take a peek at it, we can turn it around this way. Godspeed.
So we're trying not to test physics, the gods of physics.
There's a thing in space called RUD, which is rapid unscheduled disassembly, and it can happen in the case of food too.
How are you, everybody? Okay, I'm gonna share with you what I was thinking. As I was listening to Jim and all, I was thinking that how cool will be to open. Imagine that instead of that satellite kitchen, we do that, but like a gigantic bathtub, and will be the first centrifugal spa in the history that you can put yourself inside that circular amazing pool, and as it's rotating at high speeds, it will be the coolest jacuzzi in the history of mankind.
So yeah.
So anyway, that's what I was thinking. I was being creative for the next Star Wars movie. Anyway, I don't want to take, because this is a very serious moment. What they're doing there is great. What Jim has done is amazing. I'm so proud that I've been part of these classes for so many years. And used to now, I understand why all of you, and by the way, I want to say hi to Pia. I know I am in her Zoom and I didn't mention it, but I didn't mention her before, and she also deserves a big round of applause for keeping these classes going for so many years. And right now I am at the White House, which is a town in Jamaica called White House. And just I remind myself that I think in the audience we have Professor Bush from MIT, an expert on water surface tension and many other things. And I think he's there in the audience. Can we give a round of applause also to Professor Bush, who is there in the audience? Not because he's from MIT, he should be woo, okay? And that's it, guys. I love you. I will be there next, you know it. Keep enjoying that class as I enjoy learning about this satellite kitchen that Jim gave us this amazing opportunity to play and to dream about how to feed humanity in space. God bless you. Sorry, I didn't want to interrupt in the middle, but anyway, I did it. Until next time. Bye.
Thank you, Jose. Jim, is that water boiling yet?
All right. So back to science for a second. So yeah, you see the bubbles in there? Okay. We are at 4 Gs. Let me turn it down to 2 Gs. And the bubbles are a little bit bigger. And this is really cool. So now let's speed it up. So we're at 4 Gs. Now at 5, 6, 7, 8, 9, 10, 11, 12. So I'm here to tell you that we're at 14 Gs, 15, 16, 17. This water is still boiling. It doesn't look like it's boiling, but it's boiling. The same amount of heat is going into this water, the same amount of steam is coming out. But there's a really cool thing that's happening. It's like this cylinder is spinning, and when the little bubble breaks and goes up, the cylinder is spinning, so it goes up and forward at the same time. So when it goes up and forward, it dives back into the water. It's kind of like it's heat's here, and the water's spurting up, but it's going that way too, so it dives back in. And the faster you go, the faster it dives back in. And pretty soon, it's like, it's just like this. And so it's just like weird phenomena of everything just flattens out. But what this means in space is French fries, because you can fry things and not have that spatter go outside. So if you turn it fast enough, no spatter will ever leave.
That's all the cooking.
Although just the right vector will get out, but that spatter will not leave the cylinder. So, I mean, frying food in space, that's
Jim,
major achievement.
how did you... Where did this thing come from?
So I was...
Have you ever... Why did you decide to boil water in space?
Because it was easier.
Okay.
Because I was trying to melt lunar regolith to get the oxygen out.
Okay.
This is a great way to do something in low gravity. But I started to do it in my garage. And
When was that?
I was in early 2020, right at the beginning of COVID. And
So you were bored during the pandemic. You went to your garage and you said, I'm going to boil water in space?
I went and tried to melt rock.
Okay.
Melting rock's really hard.
Okay.
And it's really dirty.
Okay.
It's a lot of trouble.
So
This
instead-
is too hard, it's too expensive, too dangerous. So I'm just going to try to boil water. So I did this, and boiling water's cool.
Boiling water is cool.
You can get really geeky about boiling water. So I really got deep into boiling water, and some circumferential shear when you change the speed, and nucleation, and just all kinds of fun geeky stuff. And I got so good at it, I thought, boy, I bet I could cook food.
Okay.
So Christmas Day of 2020, I put some pancake batter in my boiling apparatus, which was like 3 generations before this. And I made like a cylindrical pancake.
Behind
and
Jim, you can see different
brought it in.
examples of cylindrical
Of course,
foods.
Christmas Day is like, who works on Christmas Day? But my family kind of understands. So I brought it in and I say, this is the future. And they're, it's Dad. And, but then they went back and they made like, blueberry pancake. It's like, this is the future. And then in honor of our neighbor, I went and I made she always used to make pineapple upside down cake. So I thought, okay, Alice's pineapple upside down cake, I can do this. And, put pineapple in and sugar, and then got that to caramelize. And then I put the pancake dough after that, cooked it up. And, it's kind of, it's not as good as this stuff. I pull it out, and so my daughter says, okay, that's good, but it's not pineapple upside down cake. That's got to be pineapple inside out cake. So that was the first pineapple inside out cake. And, food is fun, especially for an engineer, especially when you can have a machine that you can like make a pizza on your desk and not get your desk dirty. So I just went on a voyage of discovery all the way through COVID. And it was really a wonderful voyage. And so I learned so much about this, and finally got, to something that, looks like an appliance and got in a competition with NASA, got to get some funding for this, which was super fun.
Yeah, Jim placed second in NASA's Deep Space Food Challenge.
Yeah.
It was NASA and the Canadian
And
Space Agency as well.
Yeah.
Which is where these two first connected.
And we brought Charisse in. She graciously came and quick study, and we're like making pizza right there at the Ward's thing. You know, Charisse is just pumping them out, and my daughter and son-in-law are pumping them out. And then my son has a birthday, and we make a cake, and the director of the space station is there, and she sings happy birthday to my son.
And that's how you make things happen in the world, is you just happen to be in the room with the director of the International Space Station, who sings happy birthday to your son.
We do, you know, and but that was, you know, illustrates like the depth of the joy that you could have if you were in space for a year and your son has a birthday and you can eat cake on video at the same time they're eating cake. It's kind of like there's opportunity for some magic of connection back home and back with family that can come through food. I mean, it's just like what Jose is just saying all the time about. It's the core of community, is being able to eat together. So it's so fun to be on the food train with Jose and Charisse and Sam and everyone.
So that's part of what we've been doing. Charisse is the head of the R&D team at José Andrés Group for Jose. I work on the storytelling around what we do. So we've just been trying to figure out how to use these machines. When Jim reached out to the Deep Space Food Challenge, he got the tech side down. He got he knows what the machine can do and the potential for it. But I was going to try to use our equation, but I don't know if love plus hope equals a better tomorrow, but Charisse was the one who started to think through what this machine could actually do, and our R&D team has been testing different recipes. We have a few versions here, a few different things. We have the tortilla española, which is an egg, potato, and onion, sometimes, tortilla out of the machine, so that's why it's a circle, ring. We have a space pizza right there, which I think is better than anything coming out of Noakes, right? Nailed it. I went to school at Tufts. And we have a space cake. And if we can get the camera on the space cake, something that's really interesting about the work we do with...
You want to carry it over there? Take it over there, yeah.
That we're doing with this machine is that... does everybody in here like to cook? Yes. Everything we do, Charisse keeps saying this, everything we do in the kitchen has one constant variable, which is gravity, and we don't think about it. It's just, we just live on a planet with gravity. So what we're dealing with is heat and time. I'm a pastry chef, and I think I'm going to bake this thing at this temperature for this amount of time. What we have to do with this machine is also add a third variable, which is G-force. So you're going to cook this at this temperature for this time with this many Gs. So we're introducing a new dynamic which connects very directly to our lecture today about emulsions and foams, based on the fact that if you want a bread or a cake to rise, but you then have a G-force that's pushing against it, how do you balance those things? You want to keep the G's low enough to let the rise happen, and this is a chemically leavened cake. You could also theoretically do yeasted cakes, but Charisse, what's going on around the rings of this cake?
So it took a lot of cakes to get to this cake. So what Sam is saying about the G-forces is that we had to determine through trial and error and not any idea of like what a formula could give to us, because I'm a cook. I'm by no means going to understand a lot of the formulas that are put up onto the screen. So we just had to determine, okay, well, what is the time and what is the temperature that we want the very interior of this cup to be, and what determines that set point for the actual batter or for the emulsification. And then we want to go as low as we can. As soon as it begins to reach that temperature, we want to slow down the G's so that it can actually have what we would consider a rise to come and set, so you can get a very like light and fluffy cake, versus when we first did this, we were like, yeah, crank up the G's, and we got like a crepe. You know, we got like a cake that was this quantity, but it was literally about a quarter of an inch thick. And we're like, that is the worst cake ever. And so, but you know, we put so many cakes into this machine saying like, okay, we're going to do, you know, 13 Gs for 2 minutes, warm up the batter, and then we're going to turn the machine on its side, because when we were cooking through this kind of did a reverse of what normally happens.
Remember Jim's dance from before? If you can do that thing again.
Yeah, the dance. Oh. But so because
the dolphin.
So because there is the force of gravity that's pulling everything down, when this machine is seated like this, everything wants to cone. The weight wants to cone down to the bottom, right? So as you increase the Gs, it begins to flatten out. But the act of increasing the Gs is in direct conflict with what we're trying to achieve, which is a nice crumb. Which then, Jim, you haven't done it yet, but he taught us that we could turn this machine on its side.
Yes.
Okay? And then what it did is it created a flat surface now that as a cake is, so the cake will be rotating this way versus this way. And so we could lower the Gs using, what was this, momentum?
Rotational momentum.
Rotational momentum.
So
and we were able to lower the Gs and then create rotational momentum that kept it adhered to the side, but would allow the crumb to now begin to get longer. And you're going to see in this cake that it doesn't have like a round crumb. The crumb that goes through this cake is actually long. So I don't know how close you can get to that. But you see that crumb set? So that is as good as a cake can get right now that we've worked on. But nothing that we had ever seen before. We were totally shocked. And so then we went in the very other direction. It was like, how low can we go? And we went, cake is coming out of the side of we went so low the cake was just collapsing in the barrel. So, but like I say, I'm super pleased with this result today. So
we can't wait till we go to space where we can turn it to less than 1 G.
Yeah, exactly. So then you'll get all the leaven that you want.
Light.
Jim, you've been trying to get out of it, but we are going to ask you to turn that on its side and see if the water stays in, which theoretically it could, right?
Yeah. So.
And theoretically it's at boiling, so if it came out, it would be bad.
We've signed the releases.
I think so. The front row has signed the release, right?
So I have napkins at the ready.
So the water is going like this, and we turn the cylinder, the water still wants to go like this. So it could, be awful. So we have to turn it really slow so that it just gently moves it over. So
you want to sit it on the foot,
yes,
right? Yeah,
okay.
that side. Yeah, you got it.
Okay. Here we go.
A wing and a prayer. Godspeed.
We're doing okay. We're almost there.
Almost there. Done deal. How many G's is that? 11?
11 G's. Okay.
How low can we go?
Cool. Let's get some light on the topic here. Yeah.
It's still boiling.
If we turn it down, no more.
I think we've gotten is like 4. Yeah, there we go.
We're at 4 G's right now.
It's starting to wave back. Hi.
2. I don't think I can hit 2. That's going to be it.
All right, there we go. Oh yeah, look.
Right, we're at
That's
2.
good. That's 2. That's great.
Yeah. And then cranking it up. Bubbles go away. Actually, we're up the last little bit of water there. See what we get. Oh yeah,
it's a pretty good amount still in there.
That was the last bit of water.
Oh really?
Yeah. So it wasn't that dangerous after all. Okay.
One of the other results we found really interesting was learning about food and density, which we'd never really thought about. One of the chefs we work with, Chef Hector, I don't know why
That me?
wanted to make a shepherd's pie, and we did, it's technically, if it's a shepherd's pie, it's sheep on top and beef on the bottom.
Yeah.
Beef on top, or no, potato on the top.
Potato on the top. Sheep on the bottom.
Mutton on the bottom.
Yeah.
I got corrected a while ago. It's a cottage pie if it's beef instead of mutton.
Inside out.
Well, a traditional is top and bottom. So we wanted to do it in the machine, and we did the potato on the outside to caramelize, and then we did the meat. But as we spun it, we didn't realize that the meat was going to be denser than the potato. So when we took it out, they'd swapped places.
Totally swapped places in the cylinder.
Which was unexpected, but every failed result, or failure, is a place to learn. So that was really cool to see and understand, and now we can, make a denser potato or a less dense meat, I guess, somehow.
We haven't touched a shepherd pie since.
Yeah, we haven't touched it since.
I mean, that's like a thing. You could have the potato, and it's still soft, but then you could put a little wheat dough, a layer of that.
Yeah.
And then when the gluten length, then you could put the meat on top of that. Maybe it wouldn't pierce through.
Or if we put more butter in the potato.
Yeah, who cares if there's more butter? I mean, but this is the kind of thing that's like a whole new adventure to figure out how to make something new.
So these are
chocolate chip cookies. I tried making chocolate chip cookies with the chocolate chips, and I had the G's up too high, and the chocolate would melted and just went through to the surface of the cylinder and burned chocolate. It doesn't taste very good.
So we've had an opportunity to show these machines to NASA. We showed some folks from NASA on the left and cooked for them. We also showed this machine a couple weeks ago at the Air and Space Museum in DC before the shutdown, a couple days before. So, and in the center is an aspirational creation. The brownie was made in the machine, but we have this theory that instead of heating elements on the outside, you put cooling elements. You could make ice cream. Because there's an anti-griddle. There's a tool called an anti-griddle that freezes things as a griddle does heat things. So someday, theoretically, we can make that plate in the sated machine, the sated hot, the sated cold. So Jim, work on that, please.
I know. It's a
Thank you.
Great goal. It's technically
Jim,
very difficult. But
what else are you working on besides sated hot and sated cold?
Okay, so you're gonna make good food. One of the aspects of good food is like texture, crumbs, This is the type of thing you say crumbs in space, and like, oh my God, you could inhale those and get them embedded in your lungs, and there's no doctors, and you got a problem. You can get them in your eyes. You can get them in the equipment. Like no crumbs, no never. So that doesn't work with good food. So okay, we are starting to fill out the kitchen. So one way, very basic thing to fill out the kitchen with is what we call downdraft table. So the downdraft table brings air from the top and sucks it through this like tablecloth right here. And it's basically made out of filter material. So the air gets sucked through by these fans and then blown out the bottom in kind of a gentle stream around your legs. And so the speed of it coming through the top is about 1 meter per second. That's like about the right speed. So that means that if you're eating right here, making crumbs, then those crumbs are gonna go down at about that speed, 1001. And when they go down, they'll land on the table and they'll just sit there and stay. So once you finish eating, cooking, whatever would create crumbs, none of them are in the cabin air. They're all there. And so you can just take a hand vacuum, which they have on the space station, and just clean them off. And the hand vacuum has more vacuum than the surface does. So you just clean it off, you can turn the power off. And life is good if you can have chips in space, or crunchy cookies.
So Jim, why is the downdraft? I mean, I think it'd be good to explain to them why it's important to have a downdraft table at all regarding crumbs.
Well, because in space, everything's float, right? But when you have a lot of particulates, they just are a cloud of them, and these clouds tend to expand. Seems like they all have the same electrical charge, and they push apart larger and larger. So you can't not encounter a mess like this. So you just simply need to not allow that mess to exist. And so that's why having this downdraft table keeps those messes, those spills, those crumbs from going into the cabin where they're dangerous. and just landing on the top of the table.
There's a classic scene from The Simpsons. I don't know if anybody here watches, but Homer in space eating the chips,
Yes.
floating around, and then the ants get loose and get in the equipment. So this is why you need a downdraft table for the chips and the ants, right?
We could have got a placement.
We should have gotten that.
One thing that one of the things that I discovered when working for the AX-1 mission was that the crew members actually do not really get to enjoy things that are crunchy unless they are a single bite. So, or anything that's crumbs. So a slice of bread is not permitted to go into space and onto the space station, because if you bite into the bread and a crumb comes off of that, they consider that a risk to the environment. And so that same thing goes for, like a different variety of chips, crackers. None of those things can fly. What they use as bread up there is actually a tortilla. That's approved to fly. So why this becomes really important in space is that we're going to be able to give the crew members and allow them to experience what they don't typically get to experience, and what is actually, up until this gets approved or downdraft appliance gets approved into space, they will never be able to actually enjoy a crunchy item. So that's why this particular device that Jim is working through right now is really important from a culinary perspective.
Yeah. So it's cool to have the cooking appliance, but it's no good unless you have a way to control the crumbs. And it also makes things stick to the top, and so you can lay books and things out, and they stick like they're magnetic to the top. So in space, things, if you have to have control over every single thing. It becomes exhausting in space and in zero-G, because if you have 3 things, you're always trying to keep track of where they are, and so you tape them down, you Velcro them, but in natural life, as you can see, we have a lot of things. Now, if there was no gravity, can you imagine the pandemonium there would be with the things on this table, us trying to control them? So, but if the table can hold things like magnetically, then they could be setting kind of like how they are. So anyway, great. It's also going to be great for on the moon if you want to bring a moon rock in and study it, because it's going to have lunar dust on it, and you can't let that get in the atmosphere, because it's particularly, it's like silica. It's so sharp that you don't want to get in the atmosphere. But you could bring it in and work on it on this table, and all the dust would just get embedded in the top surface in a space, so you can replace that surface. Anyway, it's good for a lot of stuff other than food. So, also, yeah, a kitchen. When the last time you opened your spice cabinet, like how much stuff you got in there? You think about, okay, in space, you got to either Velcro something or tape it down, or a magnet or something. In fact, you look at all the space station pictures, and it looks incredibly cluttered. And what you're really looking at is every surface is covered with something, because you need a surface to hold something to it. So what we've done is made a space cupboard. And how it works is similar to the downdraft table, but more just the draft part of it. So the concept is right at the bottom. Oops. Let me see if I can get back here. Oh, I'm going the wrong direction. Help.
Thank you.
Yeah, thank you. Here's some books. Hey, we're going to talk about those. Here's, that. This is really cool. But let me just, here we go. Right back there. Okay. On the bottom, we have this is the fan that pulls air out. So this unit is actually pulling air inside, a flow of air inside. Again, about 1 meter a second, or a little bit faster in this case. So when you put something in, that it stays in. So you can have like dozens and dozens and dozens of things that would totally and completely overrun the space station, all just sitting neatly in here as the air flows down between them. And they're made so it won't clog the air, so this actually works. So this allows us in space to have bazillions of things, or at least dozens, whether they're toiletries or food ingredients or parts of your experiment, they're just inside a cabinet. And then when you close the door, it turns the fan off and saves power. So this is like a fundamental thing to allow you to do complicated things. What else we got?
So looking forward, I mean, what is the future of this? Is a few different things that this is why Jim and Saded and Jag and Charisse and Jose and I are working on a few different directions is how to get Saded in space. It's not in space yet. It has gone on the
Parabolic flight, thanks to Axiom.
AKA the Vomit Comet. Charisse and I were joking, we were on a flight this morning that was actually quite bumpy and felt like the Vomit Comet, but we had both space cooking devices.
Testing opportunity.
And Charisse thought maybe we should just set up a pop-up pizzeria in row 9A and see how it worked. So the idea is that we're going to start building a pantry of ingredients. You know, these are some of the things Charisse freeze-dried all weekend long to make, because freeze-dried ingredients like cheese, like sausages, are...
Just a real quick mathematical prelude to this.
Yeah, sure.
Let's say you're going to Mars, okay, and you have 20 different types of meals, okay. So, you know, large spectrum, you rotate through them 20 days, you have 20 different meal selections, and, you know, the mission is 1,000 days, so let's see, 1,000 divided by 20, so each one of these 50 times. So that's fine, unless after time 15, you decide you don't really like it, but then really that's all there is to eat. But let's say, you know, the opposite situation of scratch cooking, let's say you had 20 different ingredients. And let's just say mathematically that a food item could be made of 4 ingredients. So how many combinations of 4 ingredients are there? And factorial math, like there's almost 5,000. So in concept, you could have 5,000 different recipes, but we know all of them wouldn't be good. But let's just say we had 1,000, you know, 1,000 edible, cool recipes, and you could have a different thing every night.
Jim, who would be the person who would be putting all those ingredients together on a long-haul space mission?
You've got to have a specialist. I mean, you have to have someone that,
who's
like...
a specialist in cooking, Jim?
It's not in me. It's not an engineer. Oh, Charisse. Oh, my gosh.
Is Charisse going to be the first chef in space?
I think so.
No, I think that what Sam is actually alluding to is that when you go to the most remote areas or the most remote, you know, whatever scientific facilities, there was one in Antarctica, voyages around the world. You were talking about chuck wagons earlier today. They all had a chef, right? And right now, for any mission that goes to space, there is actually no culinarian. They just rely 100% on these pouches to provide the crew members with every single emotional fulfillment for happiness, right? That can come from eating a meal. And so, I don't know, like talking to Jose about this, we're like, chefs should be crew members, you know? Like there should be a crew member on each ship that goes out that his sole job and function is to provide not just nutrition, but, you know, emotional enjoyment, you know, to make you the birthday cake. Who wants to make their own birthday cake, right? So, but to have somebody to do that for you, and you know, that's kind of our push. I don't think it's going to be me.
But it could be you.
It could be me. I think I'm a little bit too old for that. But like I say, I think that there is a good argument as to why that should be true. And you know, we've been to a few conferences and talked with a few people that also agree with that idea. And, you know, like I say, we have proven not just using the AX2 mission as our test module, but actually going out there and talking to other crew members and talking to engineers at NASA, and they all agree the same thing. They're like, actually, yeah, we should probably have chefs on board. So if that happens, mission accomplished.
You bet. Chefs in space. It's a thing. So we're going to do a little race now because we want to get to the question and answer. We've got some special thing for the Q&A section. So let me just tell you about the environment real quick. So what we have here is a kind of environment that we've made up that is 1/6 gravity on the moon. So you see the moon out there. So the moon has got about 1/6 gravity. So this is that environment. Got radiation, so you have a window, you close it with a radiation shield. Here we have that table, we have the sated cookers. We have a special seating apparatus I'll show you in a second. Here's where we're keeping all the ingredients. We're basically in a nice, hopefully clean design that is, feels good emotionally. And we're able to have like this incredible, Jose thing of community around the table. And the stuff that just really keeps us healthy. Let's see. So, oops, a little bit of a delay here. So just looking a little closer at what there is, we see the parts I talked about before. These are things, these foods are sitting on the table. That's because this is a 1/6 G situation. If it was on Mars, it would be 1/3 G. So things could sit. If we were in space with 0 G, we would be holding these down in a different way. There's different types of receptacles that take advantage of the flow that keep the food in without getting cold. These seats right here are saddles. We call them pelvic stability saddles. So basically you mount the saddle and you press your thighs together just a little bit and they expand in between these plates. And it makes it so you have a solid place to push and pull or find things. And it's really pretty comfortable. So we can't wait to try these. Cool.